We know there are different kinds of maps. Let's look at some of the ways we think about that data. So here's a volcano. This is Augustine in Alaska. It's in the big tail of Alaska, the Aleutian Islands coming off of the mainland of Alaska. And the precursors to that eruption were being investigated. And when it calmed down, the geologists were able to go and investigate the steamy rocks. So a qualitative assessment of that would be, it's really hot and steamy. It's hard to breathe. It is got plumes of white smoke coming out of it. Whereas we need instruments to get a quantitative or numerical, something we can plot on a graph data. So we can describe the eruption and we can also measure features of the eruption. In hydrology, so if we're doing an investigation here of the interface between saltwater and freshwater at the coastline in Devon, and one thing we need to know is the topography. So using a surveying station, we're able to survey and get the exact topography along that coastline. And then we use GPR, or ground penetrating radar, that is literally going to send a radar into the subsurface, and then that is going to bounce off layers, and we can find fine layers within the subsurface of the beach and make a cross-section of the beach and the water and maybe different sediments within that beach with the GPR. We also can measure the salinity of the water through these monitoring wells, and then look at how deep is the groundwater. So these different measurements go into quantifying the relationship between the freshwater and the salty water. We can take material back to our labs, and there are different things we can do with it. One thing we can do is put different sediment sizes. So here's some sandy sediment, muddy sediment, a mix of sediments, and coarse sediments, and think about what is the porosity and maybe the permeability, the hydraulic conductivity of those different sediments and grain sizes. Another thing geologists look at, and I mentioned this before, is thinking about scales. I'm going to turn this off, of time, so temporal scales. And in water and in geology in general, there's going to be different scales. So one of those is the rising and the falling of the tides. That's going to happen on a day-to-day basis. Tectonic plates move about 2 to 3 centimeters a year. That's about the rate your fingernails grow. Energy accumulates on faults in the 10 to 100 year range. That then is released, that buildup of energy, when there's an earthquake, and then that accumulation starts again. We look at the continental crust has been depressed by ice sheets when there's a time of glaciation, when we're in an ice age. And then when that comes off, then there's a time that takes for the continental crust to rebound from that event. So looking at these other ones, there's flow of heat. There's that slow and steady falling of sediment to the sea floor. There's ice sheets advancing and retreating associated with ice ages or interglacial periods. There is the time that a volcano exists on the surface of the Earth. So like SP Crater, it's eroding, but it's still pretty young. It may not last another 100,000 years. It may erode flat. Large volcanoes can last a very long time, into the millions of years. Ocean basins, hundreds of millions of years, and the creation of them taking that long. Mountain building can be 100 million years, and then the history of the Earth, we're looking at billions. So these are the different time scales we look at. We think about time with periods in geologic history. So here's some rocks, and those are in the hundreds of millions of years old. And then these cobbles here that have weathered off of the bedrock are just in the tens of years old. Here is Meteor Crater in Arizona, and the impact and the formation of this 2-kilometer wide pit was instantaneous. So the difference is really pretty profound. When we're interpreting our geologic data, let me bring my face back. Interpreting geologic data, we look at a data set. So in this case, we have some smooth topography, and then on top of that topography are some ages. 15 million years, 10 million years, 7 million years, 4.3, and 0.6 million years. And if all we have is we have the smooth topography and we have ages of volcanism, so volcanic rocks that came out of a volcano, how could that have come about? So you can think about that for a minute, but what's come to realize is that in this area there's a hot spot. So at Yellowstone, there's a hot spot, and it is a place where there is a hole burning up through the crust, but the crust continues to move over that hot spot. So as it moves, the volcano is going to form different, it's going to form older up to younger rocks over that hot spot. Here is an observation also at Yellowstone. So I'll go back one. This is the lake right here at Yellowstone. In this image, north is now to the left, but they've observed that the area to the north here is rising as the area to the opposite side is sinking. And so if we had to think about that rising area and the sinking area, what could that be? It turns out the magma is rising beneath and deforming the crust and creating that tilt underneath the lake. Okay, so investigating geology, like any of the other sciences, involves what we call a scientific study and doing science. And the study is done by following the scientific method. So the scientific method involves an observation, observing a hypothesis, kind of explaining that observation, and then doing experiments to test your hypothesis, and then interpreting that data from the experiments. And then, did you disprove your hypothesis? Does it need to be rewritten or edited in any way? Think of a new hypothesis because your data didn't support that hypothesis. So the initial hypothesis is an explanation, and if you go through the scientific method and that hypothesis is going to withstand many tests, then we come up with what's called a theory. So a theory in science is something that it has been proven many times. If over long amounts of time that still is disproven, then that theory becomes a law, right? Like the law of gravity is the example we always use. A good theory is a simple explanation of something, and it also is going to explain a wide variety of phenomena. All right, so here's move my face again. Here's our scientific method, or our way of knowing things. So we observe. Sometimes there is a chance discovery, and we would call that serendipity, which is nice. But usually we're going to make kind of planned observations and experiments, and then we'll come up with a hypothesis. Meanwhile, that hypothesis is going to be challenged, right? So we're going to challenge the hypothesis. We're going to have in the background that other hypotheses. So just be thinking like, well, this is what I think it is, but it could be this or it could be this. And then we would revise or discard, or based on any kind of experiments that we're doing. Is it supported? No, we'll revise it or toss it out, just start over. If it keeps getting supported over time, and then it becomes a theory. Again, a theory needs those challenges, though. We don't just sit on our laurels and say, woohoo, we figured it all out. We continue to investigate and investigate. Are there other simpler theories that could explain what we've discovered? So continuing to revise and go back through our theories. Is it supported? Can we discard it? If it continues to be supported over time, then we really consider it like a scientific model and eventually a law. We can still challenge it, though. Oh, that's kind of fuzzy. Sorry about that. Once we have come up with a hypothesis and experiments and theories, we need to share that with the scientific community. We have what's called peer review, and you may have heard this maybe in the news, that science is constantly changing because we're doing more experiments and we want to share our information with other people. Other people need to be able to replicate our experiments over time. And so that replication and the investigation by other scientists is called peer review. So we, during different stages in our research, will have these conferences. So this image, why is it backwards? This image, it's kind of fuzzy, showing like a typical conference would look like. And we geologists will meet, we drink a lot of beer, we have informal discussions just in groups, and then we have a formal presentation with in a big lecture hall, and then more informal discussions afterwards. So those places we have it are AGU, GSA, the Geological Society of America, NEGC, different places where we come together and share that information.